Hello, this is Mr. Underkoffler, and today we're going to be looking at the guided notes called the real number system. You can follow along as I read the opening sentences out loud. It says the real number system represents all of the numbers that we use in pre-algebra. It consists of rational numbers and irrational numbers. The diagram below is a visual representation of the real number system. Now, if this diagram looks familiar to you, I do believe I have taught you this earlier this year. So some of this will be review. Obviously, we're going to kind of bump it up to the next level, which is the reason I'm giving you these guided notes. This ties in with what we had just recently learned on squares and square roots, and possibly also cubes and cube roots. So, real quick look at this. We have natural numbers. Natural numbers are numbers such as 1, 2, 3, 4, 5, 6, and so on and so on and so on. You can see it does not include 0. It does not include fractions or decimals. It does not include negatives. That's what the natural numbers are, and we can abbreviate this with a capital N. They're the numbers you first learned how to count with when you were a 2 or 3 year old or whatever. Whole numbers. If you look at what whole numbers are, they're almost identical to natural numbers. The only difference is that whole numbers do include 0, whereas natural numbers did not. We're going to abbreviate whole numbers with a capital W. You should notice again, whole numbers do not have negatives. Whole numbers do not have fractions or decimals. Now we have the next set of numbers, integers. Now integers are abbreviated with capital Z, not capital I, because capital I is used for irrationals, which we'll get here to in a little bit. Integers include all of the whole numbers, which is why on the diagram you'll see the whole numbers and natural numbers are inside and part of the integers. You can see that here. 0, 1, 2, 3, 4, 5, 6, and so on and so on. Those are the whole numbers. They are part of the integers. But the integers also include the negative counterparts of whole numbers. Negative 1, negative 2, negative 3, and then that goes on from there. Negative 4, negative 5, and so on and so on and so on. So that's what the integers are. Now, continuing on your guided notes. Rational numbers. Rational numbers are abbreviated with capital Q. Now, why not capital R? Because a special looking capital R is actually the official symbol for real numbers, which is what these guided notes are all about. And so we can't use capital R again for rational numbers, so we use capital Q. All right, so what are rational numbers? They are anything, any number that has the ability, that can means has the ability to be written as an integer over integer fraction. So any number that has the ability to be written as a fraction, where it's an integer as the numerator over an integer as the denominator, any number that has the ability to be written as that kind of fraction is what we call a rational number. That's the definition. And so I've given you a chart here, and I'm giving you a whole bunch of different types of numbers that you have seen so far in your life. And I'm going to prove to you that all these different types of numbers fit the definition of a rational number, because I can write them as an integer over integer fraction. The first example I'm going to give you is a whole number, 3. I can prove to you that 3 is going to meet the definition of a rational number. Why? Because I can write it as 3 over 1. That is equivalent to 3, isn't it? Therefore, it is a rational number because it meets the definition of being able to be written as an integer over integer fraction. Next, the negative counterpart of a whole number, like negative 29. I can also write that as an integer over integer fraction, can I? By writing it as negative 29 over 1. So that also meets the definition of being a rational number. Next, what about mixed numbers? Well, remember that you can make mixed numbers become improper fractions. 7 times 2 is 14 plus 6 gives you 20 over 7. So once again, I was able to write a mixed number as an integer over integer fraction, 20 over 7, and therefore mixed numbers are also rational numbers. Well, let's look now at decimals. How about a terminating decimal, a decimal that does not go on forever, but just stops, like 0.4, which is pronounced 4/10. Well, the reason why it's pronounced 4/10 is because you can write it as 4/10, which could also reduce, not that you have to reduce it, to prove that it can be an integer over integer fraction, but it does reduce to 2/5. So once again, since I'm able to write it as an integer over integer fraction, that proves that terminating decimals such as 0.4 can be classified as rational numbers. And now we have repeating decimals. Negative 3.8 repeating, meaning the 8 continues forever and ever. 8, 8, 8, 8, 8, 8, 8. Could we write those as an integer over integer fraction? Well, way back earlier this school year, I taught you how you could do this. Instead of being 8/10, if it's a repeating 8, it's 8/9. If you don't believe me, you can bust out your calculator right now and take 8 divided by 9, because fractions actually mean division problems. 8 divided by 9 will give you 0.888888888, and I think your calculator might round it off to a 9 at the end, depending what calculator you have. But that proves to you that 8/9 is equivalent to 0.8 repeating. And then from there, I can make it become an improper fraction, just like I did over here on the 2 6/7. So lo and behold, even repeating decimals can have the ability to be written as an integer over integer fraction, and therefore it fits the definition of rational numbers. So you might be sitting right now and asking yourself, well, my goodness, Mr. Underkoffler, are there any numbers that I can't write as an integer over integer fraction? Well, there are, but here's the secret. Most of the numbers that you've seen so far in your lifetime are pretty much these kind of numbers, aren't they? So almost every number that you've seen so far in your lifetime can be classified as a rational number. But there are examples of irrational numbers, numbers that are not possible to be made as an integer over integer fraction. What kind of numbers could not be possible to be made as an integer over integer fraction? Well, the most popular one is one that we just looked at in our geometry unit, and that is pi. Pi is 3.1415926, yada, 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 yada. It goes on forever, but it never repeats. So I could not write it with a repeating bar. So unlike the one that I showed you up here, that did have a repeating bar, and therefore I could write it as 8/9, you can't do that with pi. It never repeats, but it also never stops. It never terminates. It goes on forever. So any decimal that is non-terminating, but also non-repeating, meaning it doesn't stop, but it doesn't ever repeat. You couldn't write a repeating bar over the decimal part. Those kind of special decimals are the ones that are not possible to be made as an integer over integer fraction. And on the previous packet of guided notes, you also learned that square roots of numbers that are not perfect squares are going to give you decimals that go on forever but don't repeat. And they would also be classified as irrational numbers. By the way, the symbol for irrational numbers is capital I. This is why we couldn't use capital I for integers, because that gets used for irrational numbers. There's one more special kind of decimal that would fit this category of irrational numbers, and that is, forgive my poor highlighting job here, decimals like this, where it's like 0.1, then 0.1, but then 0.001, then 0.001, and so I keep putting another 0 before I put the 1. These are the kind of decimals that almost look like the repeating decimals, but they're not. You can't use the bar notation above it. So since you can't, then there's no way of writing it as an integer over integer fraction, and that's why that special kind of decimal would also fit the category of irrational numbers. All right, let's take a look at a couple example problems together. I'm going to do number 1 and 2 with you. Some of you might feel that you can do them on your own, so I'll leave that up to you. If you think you can do it on your own, then go ahead and hit pause on the video. But if not, feel free to follow along. I'm going to do number 1 and number 2 right now with you. It says, which number from the following list, A, B, C, or D, is an irrational number? And it says, don't use a calculator. Now, how can you do this without a calculator? Pull out your guided notes on squares and square roots, which also included cube roots. And you will see I gave you a big chart of perfect squares and perfect cubes. And if you use that chart, you'll be able to know how to do number 1 without a calculator. All right. I need to find out which one of these is an irrational number. If you don't remember, irrational numbers are numbers that cannot be made integer over integer fractions, and they're going to end up being these special decimals that go on forever but never, ever, ever repeat. All right, would the square root of 144 give me a decimal that goes on forever but never repeats? No, the square root of 144 is 12. In fact, if I were you, I'd write that down, that would give you 12. So since it gives you 12, that's a whole number. That's not going to be an irrational number. Irrational numbers have to be numbers like these special decimals that go on forever and never repeat, because they would not be able to be made an integer over integer fraction. 12 is going to be a rational number, not irrational. What about choice B? The cube root of 27. Is 27 a perfect cube? Well, if you go to your previous guided notes, it is. The cube root of 27 would equal 3. And so that's not an irrational number. What about the square root of 27? Is 27 a perfect square? Meaning if I square root 27, will I get a whole number answer? It's not a perfect square. 25 is a perfect square. The square root of 25 would be 5. But the square root of 27 would be 5 point some decimal that goes on forever but never ever repeats. I think that's going to be an irrational number, isn't it? But real quick, before I say the answer is choice C, let's look at choice D. The negative of the square root of 36. 36 is a perfect square, meaning the square root of 36 would give me 6. And so this would give me negative 6. That's not an irrational number. Negative 6 could be written as a fraction. That's a rational number, not irrational. So, forgive me, I went the wrong way. That is not going to be an irrational number. So, lo and behold, it is choice C. Now, there is a second part. Explain how you know. You have to explain how you know. And I basically just talked you through it. The square root of 27 is the only one on the list that does not equal a whole number or an integer. This was the one that gave you would be a decimal, like 5 point something ugly, that goes on forever, doesn't repeat. So that equals a non-terminating, non-repeating decimal, which makes it an irrational number. All right, problem number 2. Again, I'll do this one with you as well. Which number is an integer and a rational, but not a natural or whole number? Now, obviously, you need to look back at your guided notes so you can remember what natural numbers and whole numbers are, what integers are, and also what a rational number is also going to be in order to do problem number 2. Which number is an integer and a rational, but not a natural or a whole number? All right, let's start with the first part. Can I figure out which ones are going to be an integer and also a rational number? The square root of 10. All right, go to your perfect squares chart from your squares and square roots guided notes. Is 10 a perfect square? Meaning if I square root it, do I get a whole number? I don't. Would this give me an integer then? What are integers again? Integers are whole numbers, but also their negative counterparts. The square root of 10, even if I throw a negative in front, that's going to give me a decimal that goes on forever, but never, ever, ever repeats. So that cannot be rational. That's irrational. So goodbye choice A. That doesn't work. Choice B. Is that an integer and a rational? Integer. Can this be an integer? Do integers include decimals? Look back at your guided notes. No, integers do not include decimals. So, sorry, negative 29.3 cannot be an integer. Choice C. The negative of the square root of 25. Well, the square root of 25 is 5. And then you keep the negative in front. Is that an integer and a rational? Yes. Choice D, 25. Is that an integer and a rational? Yes. So the answer to this problem is either C or D. but I need to find one that is not a natural or whole number. So which one of these is not a natural number and is not a whole number? Do you remember what whole numbers and natural numbers do not include? They do not include negatives. So this one right here is not a natural number or whole number because it has a negative part to it. But it's still an integer and a rational, and therefore it is the answer to problem number 2. Now I'm going to admit that's one of the trickiest problems on this page because of the very complicated parts of the directions here. All right, let's move on. Problem 3 and problem 4. I would like for you to do these on your own. So hit pause on the video, do 3 and 4 on your own, then hit play when you're ready for me to go over it. It says, all right, so I'm going to go over these now. I hope you've already done these on your own. If not, you better hit pause now. So here I go. Problem number 3. If the square root of n is to represent a rational number, which of the following values could not be a value of n? It says no calculator. All right, so the square root of n, it's supposed to equal a rational number. Do you remember what rational numbers are? Rational numbers are numbers that have the ability to be written as an integer over integer fraction, which is almost every single number you've seen so far in your life, just not the decimals that go on forever but don't repeat. Okay, so with that in mind, if the square root of n is supposed to be a rational number, which values could not be a value of n? All right, so would the square root of 49 equal a rational number? It would, because the square root of 49 is 7. So that could be a rational number. I'm trying to find which one of these would not be a possible value of n. Well, 49 could be a value of n. So that is not going to be an answer to this problem. I'm trying to find the one that is not going to be a value of n. So goodbye 49. Let's see. What about 50? The square root of 50. Ooh, that would not be a whole number, would it? Because the square root of 49 is 7. The square root of 50 would be something a little bit higher than 7. That would be a decimal that goes on forever and does not repeat. That would not be a rational number. So I think that's going to be the answer to this, because that would not be a possible value of n. But let me just real quick, let me look at C. The square root of 100 would be 10. That would be a rational number. So that could be a value of n. I'm trying to find which one could not be a value of n, so that's not going to be the answer. Is 256, is that a perfect square? The square root of 256, yeah, that would be a perfect square. So that would equal a whole number. You can find it on your list of perfect squares from your squares and square roots guided notes. So that would be a rational number. I will need to find one that's not going to be a value of n. So lo and behold, that would be choice B. These problems that have the word not can be quite tricky. I'm going to be honest with you. You have to read them carefully. Problem number 4, explain or prove why 0.27 repeating is not an irrational number. Well, if it's not irrational, then it is rational. How can I prove that a repeating decimal is rational? Well, the way you prove it is you use the definition. A rational number is anything that can be written as an integer over integer fraction. Why don't you show how you can write the repeating decimal as an integer over integer fraction? That's all you have to do to prove number 4. So did you do that? Did you show that 0.27 repeating can be written as 27/99, which is an integer over integer fraction, and that proves it's a rational number, which makes it not irrational. And that's how you would pretty much prove number 4. All right, moving on. Comparing and ordering rational and irrational numbers. The following tips can help you put numbers in order or to compare them. First tip, make each of them decimals, then compare them using place value like tenths, hundredths, thousandths. Next tip, think about where the numbers would be on a number line. All right, problem number 5. The locations of 4 points on a number line are described below. So they tell you point A is the cube root of 150, point B is the fraction 21/4, point C is 9/5 times pi, that's what I mean when it's next to pi. Point D is the square root of 30. All right, part A, write these numbers in least to greatest order. Use a calculator. Show the work. All right, I hope you know where the cube root symbol is on your calculator. We talked about this before, and I hope you know where the square root key is on your calculator. You could also use your cell phone if you turn it sideways with the calculator app. I know if you have iPhones, you can do this. You can get square roots and cube roots. If you use your computer's calculator, I think it also, if you has a scientific calculator mode that you can use to get square roots and cube roots. So there are your options for calculators. Do part A on your own. Hit pause on the video, do part A on your own, then hit play when you're ready for me to go over it. Okay, I hope you've done part A on your own. It did say to show the work, which means you better tell me what the decimal values are when you use your calculator for each of these numbers. All right, here I am going over the work. If you didn't do this yet, you better do it now. Hit pause if you need to. Here I go. The cube root of 150, which is point A, that would equal 5.313, yada, yada, yada. That's me using my calculator. 21/4 is the decimal 5.25. Doesn't go on forever. It stops. It's terminating. Point C, 9/5 times pi is 5.654, yada, yada, yada. And then point D, the square root of 30 gives me a decimal that also goes on forever, 5.477, yada, 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 yada. I need to put these numbers in least to greatest order. All right, they all start with 5, don't they? So what's the next number according to place value? 5.3, 5.2, 5.6, 5.4. Well, 5.2 is smaller than 5.3 or 5.4 or 5.6. So that means the 5.25, which is 21/4, that's the lowest. Who's next? 5.3 is smaller than 5.6 or 5.4. So the cube root of 150 is the next least number. Because it did say least to greatest order, didn't it? I hope you didn't put it in greatest to least. Next, I only have 2 more choices left. Is it the 5.4 or the 5.6? It's the 5.4, which was the square root of 30. And then lastly, we have 9/5 pi, because that was 5.6, and that's bigger than 5.4 or 5.3 or 5.2. So that's your answer for part A. Notice I wrote the answers in the original forms of the numbers, not the decimal forms. I hope you did that as well. All right, part B. I would like for you to do this on your own. Hit pause on the video, then hit play when you're ready to do this on your own. For those of you who do not have these guided notes typed up for you, I think I already made the number line for you. If not, here's a hint. All these numbers are between 5 and 6, aren't they? So I would start at 5, then label the hash marks in your number line as 5.1, 5.2, 5.3, 5.4, 5.5. Count by 1/10 in between every single hash mark. That's the easiest way of doing this. All right, do part B on your own. Hit play when you're ready for me to go over it with you. Okay, I hope you've done part B on your own. It said graph the points that are irrational numbers. If you have already forgotten, irrational numbers are the ones that are not possible to be made as an integer over integer fraction. And they are the decimals that go on forever but never, ever, ever repeat. So I only want to graph those numbers, the irrational ones. I got news for you. 21/4 is rational, not irrational. But the other 3 were the irrational numbers because they were the decimals that went on forever and did not repeat. So we are only going to be graphing point A, point C, and point D because they were the irrational numbers. Point B was rational. So we're not graphing point B. Okay. Here's how it should look. Since point A was just a little bit higher than 5.3, it goes a little bit to the right of 5.3's hash mark. Point C was 5.65. That is almost halfway between 5.6 and 5.7 because 65 hundredths is about halfway between 60 hundredths and 70 hundredths. So that's why it's pretty much at the halfway point between 5.6 and 5.7. If you did not have it at the halfway point, erase it and fix it. Point D, since the square root of 30 was 5.47, 5.47 is closer to 5.5 than it would be to 5.4. If it was 5.41 or 5.42, then it would be close to the 5.4 hash mark. But it's 5.47, which is going to be closer to the 5.5 hash mark. That's why the dot is closer to the 5.5 than it is to the 5.4. And that's how you do part B. All right, moving on. 6, 7, and 8. I would like for you to do these problems on your own. It does say to use a calculator, and it does say to show your work. When I say show your work, I mean tell me what you get from using your calculator, so that way you can prove to me to justify your answers. So make sure you do that. All right, hit pause on the video. Do these problems on your own. All right, I hope you've done this on your own. Here I go, going over the answers. Number 6, if I use my calculator, 7/11 is 0.63, repeating 0.636363. So that's the decimal value of that. The square root of 44 gives me an ugly decimal as well. Now, how do I know which one is where? I actually advise taking this to the thousandths place value. Why? Because the tenths are both 6s. The hundredths are both 3s. So in order to compare them, I need to find the place value where they're different. And the place value where they're different is in the thousandths. 6 thousandths is bigger than 3 thousandths, isn't it? So I bet you're going to put greater than. Wait a minute. They're negatives. Negative numbers go in the reversed order of positives, meaning a -6 is actually less than a -3. And that's why this is less than, not greater than. If you accidentally put greater than, that's because you were thinking positives. These are negatives, so tricky Underkoffler here giving you number 6. They are negatives, be careful. All right, number 7. Did you show the work? 6/25 is the decimal 2400ths, 0.24. The square root of 0.0576, again, I expect you to use a calculator, is also 2400ths. Therefore, I prove to you they are equal. All right, problem number 8, putting the following numbers in least greatest order. Again, did you show the work? Did you show me the decimal values of each of these numbers? The cube root of 360 is 7.113. If you did not get 7.113, I bet you accidentally did the square root of 360 instead of the cube root of 360. So please be careful. Make sure you did your cube root function of your calculator or computer's calculator or cell phone's calculator. 1/9 is 0.11111. I don't need to show work for 7.15 because it already was a decimal. I could have maybe written it with the 0 in the end, since I seem to need to go to the thousandths place value here to compare and order these. So you might have written a 0 in the thousandths place value here to help you on these problems. I don't know. And the last number, square root of 50, is 7.071, yada, 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 yada. So I need to go in least to greatest order. Who is the least? It's the one that had a 0 in the tenths, because all of these numbers start with 7, don't they? But 7.0 something is going to be smaller than 7.1 something. So that's why the square root of 50 is the smallest number out of these 4. Now, all of the rest of them start with a 1 in the tenths. So I need to go to the hundredths. Which one is different in the hundredths? Oh, this one here, the 7.15. So that's going to be the biggest number. You can put that on the far right. You'll notice the next ones had 1s in the hundredths. So I need to go to the thousandths to see who's bigger. 3 thousandths is bigger than 1 thousandths. Therefore, 7 1/9 is the second smallest number. So that should be second. 7.113, which was the cube root of 360, is the third number, going least to greatest order. And I already told you 7.15, that's the only number here that had a 1 in the tenths, but then a 5 in the hundredths. So that's the biggest number of this group, and that makes it the greatest. All right, the very last part of your guided notes is on solving equations using square roots or cube roots. Follow along with me. If x to the second power equals a, then x, plain old x, not x squared, but just plain old x, would equal the positive or negative of the square root of a. That actually means two different answers. Positive or negative means it could be positive or it could be negative. So when you get the square root of a, it could be the positive of that answer, but it also could be the negative of that answer. That's two possible answers. Now why? Why could it be either positive or negative? It's because, yes, a positive times itself would equal a positive, but a negative times itself to the second power could also equal a positive number. So what I mean by this is, say that a is 64. The square root of 64 would be 8. But negative 8 would also work, because negative 8 to the second power would mean negative 8 times negative 8, which also would equal 64. So that's why if you have x squared equaling a number, then x is going to equal not just the positive answer from the square root of the number, but also the negative answer for the square root of that number. You'll see what I mean when we get to some examples here. Right now might be a little unclear to you. You'll see what I mean when we get to examples. If the cube root of x equals a, then x is just going to equal the cube root of a. Now, why doesn't it have the positive or negative symbol like the other rule did above? Here's why. If I take a negative number to the third power, it does not equal a positive. It actually equals a negative, because a negative times a negative is a positive, but times a third negative puts it back to a negative answer. So that could not work if x to the third equaled a regular positive a. So unlike the x to the second power type of problems where you have to have a positive or negative answer, if it's x to the third power, the negative answer is not going to help you here, because the negative number to the third power actually equals a negative, not a positive. And again, if that doesn't make much sense to you, you'll see what I mean when we get to some examples. All right. Real quick, before we get to problems 1 through 8, little follow-up question. Why didn't we use the positive or negative symbol when we were solving problems using the Pythagorean theorem? Do you remember Pythagorean theorem? Pythagorean theorem is when we had a squared plus b squared equals c squared. On those problems, we would get things like x squared equals some type of answer at the end, and we would have to square root it. But when we did that, we never used the positive or negative symbol. Why didn't we? Well, do you remember what the Pythagorean theorem was actually used for? It was used for finding the measure of a side of a right triangle. Can right triangles have sides that are negatives? No. That's why we didn't use the positive or negative symbol when we did Pythagorean theorem problems. That's the only reason why, because you can't have negative side lengths. So keep that in mind. If you are dealing with a real-life scenario problem or a problem dealing with geometry where the negative answer does not make sense, then you're going to pretty much ignore the rule then that I talked about earlier with if x to the second power equals a, then you have to include the positive or negative of the square root of a. You would not use that if negative answers don't make sense. And that was the case with right triangle sides, and that's why we didn't use the positive or negative symbol for the Pythagorean theorem. All right, let's go ahead and take a look at numbers 1 through 4. Now, the directions say solve, round to the nearest tenth if necessary. You may use a calculator, but only use it when necessary. Hint, if I'm giving you numbers that are perfect squares or perfect cubes, you could go back to the guided notes on squares and square roots and cube roots and use the charts on perfect squares and perfect cubes to help you do these problems where you wouldn't have to use a calculator. I do believe for those of you who have the typed up guided notes in front of you that 1 through 4 are already done for you. I'm going to talk you through them though right now. Problem number 1 says this x to the second power equals 21. So how do I do this? Well, I can use the rule that I learned from above, that if x to the second power equals a, then x would equal the positive or negative of the square root of a. Square root is the inverse of taking a number to the second power. So we're going to do that to solve for x, because the inverse of the second power is the square root. So the square root of 21, you're going to have to use your calculator for this because 21 is not a perfect square. So the square root of 21 is not going to give you a whole number. If I use my calculator, I'm going to get 4.58. The directions say round to the nearest tenth. So what would 4.58 round to? It would round to 4.6. But since I have to include the positive or negative of the square root, then it's going to be 4.6 or negative 4.6. Notice I use the approximately equal to symbol because these are rounded answers. Whenever I round, you should be in the good habit of using the approximately equal to symbol. Again, if you don't know why the answer could be positive or negative, it's because if you take a negative number to the second power, that means the negative times itself, and a negative times a negative would equal the positive 21. That's why we have to include not only the positive answer, but also the negative answer. All right, problem number 2. 324 equals y to the second. So how do I solve for y? Well, I do the square root. But again, we have to do the positive or negative of the answer. So the square root of 324, that actually is a perfect square. If you went back to your guided notes that had the list of perfect squares, 324 is a perfect square. The square root of it is 18. Again, we want the positive or negative of the answer, so it's positive 18 or negative 18. Normal equal sign because I did not have to round. Problem number 3. K to the third power equals 1,728. Third power, not second power. So we need the cube root, not the square root. The cube root of 1,728 would be 12. Now that one I would expect you to use a calculator on. I do not expect you to have memorized or using your guided notes for a huge number like 1,728. The cube root of that is 12. Now why am I not doing the positive or negative symbol on problem number 3? Because if I thought that negative 12 would work, then that would mean that negative 12 to the third power would equal a positive, and it doesn't. Because a negative times another negative actually gives you a negative answer, not a positive answer. And that's why we do not use the positive or negative symbol for cube root answers for when there's x to a third power, because it would not equal the positive number on the original equation. All right, problem number 4 is a little bit different than 1, 2, and 3. Do you see how 1, 2, and 3 only had the variable taken to a power and that's it? Nothing else was happening to the variable? Well, in problem number 4, it's not just n to the second power. The n to the second power is also being multiplied by 5. So when you're doing inverse operations, you need to go in the opposite order of PEMDAS. You might remember I used to call that SADMAP. It's just opposite of PEMDAS. So you need to subtract or add first if there's subtraction or addition. This problem does not. Then you would divide or multiply next. Ooh, this does have n to the second power being multiplied by 5. So you need to divide by 5 first to get the n to the second power being isolated by itself. 180 divided by 5 is 36. Now I do the positive or negative square root of 36 to get the answer to this problem, and that's going to give me 6 or negative 6, and that's how I do a problem like number 4. All right, with that in mind, I want you to do 5, 6, 7, and also word problem number 8 on your own. Hit pause on the video, do these problems on your own, then hit play when you're ready for me to go over the answers. All right, I hope you've done these problems on your own. I am now going to go over the answers. Here we go. Problem number 5. You should do the positive or negative square root of 900. That's going to give you positive 30 or negative 30. Problem number 6. Did you do the cube root, not square root, cube root of 64 because it was d to the third power. No positive or negative symbol should be here. That positive or negative only should be used when it's a variable to the second power, because a negative number to the second power could also equal a positive, but that does not work with third power. as I've explained already. So this is just going to give you the answer of 8. That's it. Negative 8 would not work. Problem number 7 is kind of like problem number 4. You need to divide by the 3 first. Then that will give you c to the second power by itself, and that equals 75. Then you do the positive or negative square root of 75, and this is going to give you a decimal. You're going to have to do this in your calculator, then round it to the nearest tenth. And if I use my calculator, the square root of 75 was 8.66 and so on, and that's why it rounds up to 8.7 or negative 8.7. Last problem, number 8. It said a tsunami is a long, high sea wave caused by an earthquake on the ocean floor. The speed of a tsunami can be measured by the formula, and you can see the formula right here. It tells you S is the speed of the wave in meters per second, and D is the depth of the ocean in meters where the earthquake will occur. All right, what is the speed of a tsunami if an earthquake occurs at a depth of 632 meters? Round your final answer to the nearest tenth. Use a calculator. All right, so we start with the formula. Now we got to substitute. Where do I put the 632? That is the depth in meters. That should go in for the D. So I hope you realize that. Now, this is kind of like number 7 and number 4, where there's more than just a variable being taken to a power, but there's also another mathematical operation involved. It's being divided by 632. What's the inverse of division? Multiplication. So use your calculator. 9.61 times 632 gives you 6,073.52. Now we're going to take the square root. Whoa! Why don't I have the positive or negative symbol? Because the negative answer does not make sense. What was the problem asking for? What is the speed of the tsunami and the speed is always going to be, if you look above, in meters per second. Ladies and gentlemen, that speed should be positive, not negative. That's why I'm not using the positive or negative symbol. I only want the positive answer. All right, use a calculator and round to the nearest tenth. If I take 6,073.52 and I square root that, I would have got 77.93. Since the 3 in the hundredths is lower than 5, then this does not round up. It just stays 77.9. Make sure you put meters per second, or m/s for meters per second, and the approximately equal to symbol. All right, guys, a long video. Thank you for going through this. We'll see you next time.